Hey, let's start class. So today we will talk about classification and regression tree. Um, Before we started, I will just mention that I've already posted the midterm group project and presentation announcement in the Moodle. And take a look. We will form groups, work on an independent data set. You can, if you have research data available, that's the best. Just work on your research data because you are very familiar with that. And you can, of course, do some research, and it's easier for you to interpret and to get the meaningful results. If you cannot find any research data from your study, you can download some public available data set. I have some links in the announcement so you can look for some data. And also, the group should be contain about 3 to 4 students. And if you cannot find your group mate, uh, I have already had posted a forum, so you can go to that forum and then post it that you are looking for some teammates and to see who are interested to join your group, or if you are interested to join others group. And I've already posted, so each presentation should be about 15 minutes, and every team member should involve actively and also should involve in the presentation. And I see this is a very good opportunity for you to present your study and also to apply what you learned. Um, and the date is October 28th and 30th. So you still have about 4 weeks to work on that. So we will still talk about the trees, bagging trees, random forest, these things. So you can start to look for the data set and find your teammates, and then you can uh, start it maybe 1 week later and to find some methods that you can apply to a data set. Okay, and let me know if you have any questions. And also, I've posted homework 4 on the Moodle. So homework 4, that's probably the last one. So work on that. It's due next Thursday. Okay. And then after homework 4, you will have presentations for the midterms. And after midterm presentations, you can work on the final project. And I will announce the final project and presentation later. And also we have and you should prepare for the final exams. Okay. So that's the logistics for this course. Any questions? Okay. So let's talk about the classification and regression tree, which is one of the most popular data mining method. So start with classification tree. So this is a famous data set called IRIS data set that gives the measurements in centimeters of 4 variables. The sepal length, width, and petal length and width for 3 species of iris. And each species contains 50 flowers, 50 measurements. So these 3 species are Setosa, versicolor, and virginica. So the purpose is to use these 4 numeric measurements to classify the flower belongs to one of the 3 species. Okay, and this shows a tree results. So from a tree diagram, and you can see that one of the good things for the for the tree method is what? It's very easy to see the model. So that's important, right? When you have a data set, you apply some method, it will be much easier for the user to understand the model if you can see the model. And that is actually not that common. We can see the model like through the regression models, linear regression models, GAN, but there are many models you cannot easily visualize that. Like later you will see like a random forest, bagging trees, artificial neural network, deep learnings. So these models, there are many machine learning algorithms and statistical models which you may not be able to see the model very clearly. But tree is one of the few that you can easily see that. Okay, so here you can see a tree model through a tree diagram. Of course, this is one types of the tree diagram, and we will see some different types. So start from the top. We call it from the top. We call it that's the root. Okay, root contains all the samples in the data set. And then it starts with the splitting. That's the root splitting. Okay, so we use the pitot length to do the split. If the sample has the pitot length is less than 2.45 centimeters, then it goes, if the condition satisfied, it always goes to the left branch. If the condition does not hold, it goes to the right branch. Okay, and for the samples that with the pitot length is less than 2.45, we stopped here. Then we say these are we predict as a setosa. Why? Because we have 50 observations that falls into this branch. And all of them are setosa. And you may ask how I can see that. You can see we have 3 numbers separated by the slash, right? 50, that's the number of observations from the setosa. And that's what we predicted. Okay? And if the pitot length is greater than or equal to 2.45, then we go to the right branch. For the right branch, we have a further split using the pitot width. If the pitot width is less than 1.75, then we will predict as a versicolor. Why? Because we have 54 observations falls into this. 54. But among these 54, 49 of them are versicolor. So we predict as versicolor. And there are 5 actually belongs to Virginica. But to do the prediction at this node, we prefer to use the versicolor. Why? Because this is the dominant class, majority votes, right? So if the pitot width is no less than 1.75, then we predict as Virginica because we have 46 samples, and among them, only one of them falls into the versicolor, but the rest 45 goes to the Virginica. So you can see, we can easily see that, right? And also how to interpret that. The interpretation is very simple. You can use if, else, then language, right? If the pitot length is less than 2.45 centimeters, it is setosa. If the pitot length is no less than 2.45 centimeters but the pitot width is less than 1.75, then it's versicolor. Otherwise, it's Virginica. You see that? This model can be easily translated to if, else, then language, right? So that is very logical, right? And easy to express and interpret. And you can actually see the models, okay? And this is right-hand side, it shows a plot that shows the splitting through the tree models. So you can compare these two. This is the tree diagram, left side. Right side is the splitting of the X space through the tree models. So what is the X space? In this X space, we have 4 variables, but we only use these 2 variables, right, in the splitting. So why not we just use these 2? So the horizontal is petal width and the vertical is petal length. So what is the first split? The first split happens here. You see that? That horizontal line is at 2.45. Okay, so if it's less than 2.45, you can see all these samples less than 2.45 centimeters for the petal length, they belongs to the setosa, right? And then what's the second split? Second split happens here. You see that vertical line? So that split the 2 class. Okay, and you can see for this, what is that? This is the petal width is greater or equal to 2.45, and the petal width is greater than 1.75. So that is the virginica, right? So this area corresponds to virginica. And these are the versicolor group. But you can see we have some cross. Some samples are crossed. And here we have 4 virginica that has the petal width is less than 1.75. And also we see there is a one versicolor that, let me see. You cannot see that. The one that cross is here. You can see there's a blue cross here. Okay, so there's one versicolor that has the petal width is greater than 1.75. Okay, but anyway, you can see these matches. So you can see what is the nature of a tree model. So the nature of a tree model is what? It's just partitioning the feature space or the X space into those rectangular regions, right? And then we predict each rectangular regions based on its majority class, right? So since this is dominated by versicolor, we predict at versicolor. And this is setosa and this is virginica. So that's a tree, okay? Okay, so regression tree. So now this one is the Major League Baseball players' salary example. We have 322 players, and we have their number of years played in the major leagues, and the hits, that's the number of hits made in the previous year. And the response is the salary measured in 1,000s, and also we did the log transformation. Okay, so here you can see the root is before any split, we have a root here. Okay, then the first split is using the year. If the number of years played in the major league is less than 4.5 years, then you can see the pay, of course, is in the log transformed in the unit of 1,000, is 5.1. And we have 90 players. Okay, and if the number of years is no less than 4.5 years, then we have a further split at the number of hits that played in the previous year. Okay, if the number of hits in the previous year is greater than 117.5 or equal to that, we have 6.74. But if it's less than, we have 5.99. So you can see that's a tree model. And you can see it's easy to interpret, right? So for these three, we call it terminal nodes, also called the leaf. Okay, so these terminal nodes also called the leaf. So why this is called a tree? Tree is really the tree diagram is actually an upside down tree. So the root is at the top, leaf is at the bottom. Okay, so for these three leaves, you can see which one has the lowest pay. Lowest pay is here. That's 1, 2, 3. So what you can see is a very simple and intuitive interpretation is what? So the main factor that determines the pay is what? Is the number of years that the player play in the major league. So 4.5 seems to be a good cutoff, right? If the player plays in the major league less than 4.5 years, has the lowest salary. If the player is a senior player, let's say play more than 4.5 years, then that depends on the player's performance. If the performance is not that good, and you may ask, how do we measure good or not that good? We use 117.5. Okay, if the number of hits is less than 117.5, then that's the pay. So the player has the median pay, right? If the player plays very well in the previous years, then it has the highest pay. You see that? That's a very intuitive and simple interpretation, right? And this shows the partitioning of the X space. We have the years and hits. So the first split is at the year. So you can see that is these vertical lines. See that? That at 4.5 years. If it's less than that, we have these. So these players have the pay is based on that, right? So that region corresponds to this leaf. Okay, and what about this region? This region corresponds to this leaf, all right? And what about this leaf? This leaf corresponds to this region. So just as I said in the classification example, the nature of a tree diagram, a tree model is just partitioning the feature space into those rectangular regions. Of course, here we just have two variables, so we can call it rectangular. If we have more than two variables, then we can call it as a hyper rectangular regions in higher dimensions, right? Okay, so that's the illustration of the two types of trees, models, regression and classification. So there were some tree-related terms. Root, we've already explained. Root is the point without any split. So the root is the starting point of a tree. Is the top, is at the top of the tree in the tree diagrams without any split. Then the leaf is the terminal nodes. So leaf, we stop there. We don't have any further split at the leaf. Okay. So what is internal nodes? Internal nodes are like this is an internal node. So for these nodes, it's not the root. It's not the leaf. It's somewhere between. It has a splitting for the internal nodes. Okay. And the tree size. Okay, that's tricky. So how do we measure the size of tree? And you may ask, why we need the tree size? Because the tree size is very useful. Because we need to have some measurement to quantify the complexity of a tree model, right? Remember, we have AIC, BIC, those. So we need to have some idea about how complicated this tree model is. Okay, so let's see if we have a tree model like that, how do you quantify? Is this a very simple tree or very complicated tree? Right? So a very simple and also intuitive way that to quantify the complexity of a tree is what? Is just count the number of leaves of a tree. So here we have 3 leaves. So that number of leaves of a tree is the tree size. Let's say if we have a tree with 1,000 leaves, so the tree size is 1,000. This, we know for sure this is a very, very complicated tree because it has 1,000 terminal nodes. But if we have a tree like that, 3 leaves, so the tree size is 3, we know this is a very simple tree. Does that make sense? So this is the tree size is used to quantify how complicated the model is. And we will use that concept in a minute, okay? So that's the tree size. And then the next one is the tree depth. Okay, why we need to have a depth? So the tree depth is related to the interaction order. Okay, so I assume you're familiar with regression model and ANOVA. So in the regression model and ANOVA, we know we can include interaction in the regression model or the ANOVA, right? For the interaction, there were several types of interaction, depends on the order. Okay, for example, we can have a two-way interaction, like if you have an ANOVA model, analysis of variance model. Okay, so you can include the two-way interaction. That means it has interaction between 2 explanatory variables. And you can have a three-way interaction. That may include 3 different explanatory variables. And you can have a 4-way interaction and so on, right? So the order of interaction depends on how many variables involved in that interaction. Two-way interaction, the order is 2. Three-way, order is 3. Four-way, order is 4, right? That is related to the interpretation of the models, particularly how complicated that interaction can be. Okay, so now the tree depth is related to that concept. So let's say if we have a single split, tree, just stop at the first split. So we have only 2 leaves. The depth of this tree is 1. Why? Because we only have 1 split. And the depth is 1, the tree depth is 1, that corresponds to what? This is a main effect model. There's no interaction. Only 1 split, only 1 variable in, right? Okay, now let's see for this model, what is the tree depth? So the tree depth is 2. Why? So the depth of a tree is the maximum number of splits that needed from the root to the leaf. Okay, so here, for this tree, if we reach this leaf, how many splits we need to have? We just need to have 1 split, right? Just have the split at the year. Then we reach that. But that's not the maximum. The maximum is actually these 2 leaves. How to reach these 2 leaves from the root to this? We need to go through 2 splits. Does that make sense? First is the year, second is the hits. So we need to have these 2 splits to reach from the top, which is a root, to the bottom. So that's the maximum number of splits we have. And that's the tree depth. So that means what? So if a tree depth is 2, that means what? So that means this tree model can contain at most 2-way interaction. So it can hold up to 2-way interaction. Because for these 2 leaves it involves the interaction between the year and the heat. Does that make sense? So you can see the depth of a tree is related to the order of an interaction. Okay, so now let's just see another example. So let's say, for example, now based on this tree, I have a further split. Okay, so what is the depth of this tree? Okay, so now you can see what is the deepest leaf we have. The deepest leaf we have is here, these two. So how many splits we will have? From the top, let's say 1 split, 2 split, 3 split, and 4 split. So we need to have 4 splits to go to these 2 leaves. So the depth of this tree is what? Is 4. So that means this tree can contain the order of interaction up to 4 way. Okay, so that's the depth of a tree. Okay, so the tree, as I said, is basically partitioning the feature space into a set of rectangles and fit a very simple model. For a regression model, it just uses a constant. You can see for the regression model, it used a constant. For the classification, it used a majority votes. Okay, and a tree is constructed in 2 steps: growing tree and then pruning a tree. So step 1 is to grow a tree, and step 2 is to prune a tree. And we will talk about details in a minute. A key advantage of a tree, that's classification and regression tree, is its interpretability. So the feature space partitioning is fully described by a single tree through a tree diagram. Okay, a card is implemented in our part library, and also there's a library called the tree library. And a major competitor for the card is C 5.0. So C 5.0 is developed from the computer science area people. And the R part and the tree library is developed from the statisticians side. So they are very similar, but there are some slight differences. I will talk about some more details later. Okay, so this is related to, so the tree basically partitioning the feature space into a set of rectangles. So can we get a splitting like that? No, we cannot. So this is not doable by a single tree. So it can partitioning the feature space, but this is not possible. And you can easily see that why. Okay, because what's the first split? The first split has to be either like this or that across all the ranges of X and Y, right? So, but this doesn't happen. So this is not possible. But later we will see this could be achieved through like multiple trees. It's not achieved, it's approximated through multiple trees. And we will talk about that later, okay? So when we reach the ensemble models. Okay, now let's talk about how to build a tree. So as I said, the tree has 2 steps. So the first step is to grow a tree. So we use the recursive binary splitting to grow a tree on the training data. And when we will stop, and what do we mean the recursive? So the recursive means that we repeatedly applied an algorithm. Okay, so that's called recursive. And that algorithm here in the tree is binary splitting. Okay, so here you can see when we fit a tree, like this is a tree. Okay, so what we do is we first do the binary splitting here, right? Then we have the number of samples falls into this. Then we do a binary splitting here, and we do a binary splitting here, and we do a binary splitting here. So you can see to construct a tree, only we need one algorithm just to do the binary splitting. and we repeatedly applying this binary splitting algorithms. Okay, but the question is, when should we stop? Right? So there are some stopping criteria which we will talk about in more details. We will stop only some of the terminal nodes that has fewer than some minimal number of observations, or if we set some other stopping criteria. So if at least one of the stopping criteria was met, then we stop growing a tree. Then we stop there. Okay? But that's not the final model. The final model is we need to have our second step. That's pruning a tree. Okay, so and then we apply the cost complexity to prune a larger tree in order to obtain a sequence of simplified trees. Okay, so, and as a function of alpha, we will talk about what is alpha in a minute. And the alpha is a tuning parameter. Okay, and how do we find the optimal tree? Because we have a sequence of trees. We need to find the best tree through the k-fold cross-validation. So you can see cross-validation is very important, right? To choose the optimal alpha so that we can find the optimal trees. Okay, so basically a tree contains 3 steps: growing a tree, pruning a tree, and then finding the best tree. So growing a tree means we do the splittings until we have a very, very complicated tree. But this tree may be overfitting. It's too much. It's too complicated. So we need to simplify the tree a little bit. So we created a sequence of simplified tree through the step 1, based on step 1. And then which tree we should use? That's the step 3. We should, based on the cross-validation, to find a best tree. Okay, so that's the tree algorithms. Okay, so how to grow a regression tree in step 1. As I said, this is just a recursive binary splitting algorithm. So the idea is just using a very simple algorithm, just do the binary splitting, and we repeatedly apply that. Okay, so we only need to consider how do we binary split. And you may ask, why we need to have a binary split? Why it's binary? Okay, so why we just have two arms? Why we cannot have like a 3 arms, 3 branch? Can we do that? Yes. There are some tree algorithms that can do the multi-way splits. However, the mainstream or most of the tree algorithms, they do binary splitting. Why? Because the multi-way splits has a problem. It splits the data too fast so that it leaves insufficient amount of data points at the next level. So we don't want that to happen. So that's why in practice, you can see almost all the tree algorithms using the binary splits. Okay, so how do we find the optimal splits? That actually boils down to 2 questions. First question is, we need to find out which variable we should use, because we have a lot of choice. We have a lot of variables, right? And also for that variable, what is the splitting point we should use? Okay, so that by answering that, we can find out what is the optimal splitting, binary splitting, right? So how do we do that? So let's see. This actually is through the exhaustive search. And at first, you may think, wow, this is a very computationally intensive algorithm because it's doing exhaustive search. But that's not too bad. Why? Because remember, the tree algorithm that the sample size decreased very quickly. So for this split, we used the sample size is all the observation in the training data. But for this one, it only includes part of the data. So you do the exhaustive search for this split, you just use a subset of training sample. If we have a further split, then we have fewer samples need to worry about. So the sample size decrease very fast. So that's why tree is always considered as a very computationally efficient algorithm. So tree can be easily adapted to the big data. Okay, so that's actually one of the advantages of using trees. So it's not too bad, it's exhaustive search. But also exhaustive search is not that complicated. Why? Because let's just first think about the regressions. Okay, so for a regression, okay, for a regression, we fit a constant C1 and C2 at each node, at each leaf, right? So let's say we do a split and then we fit a constant. Suppose we have a split, okay? We have 50 observations that falls into the left branch and the 50 falls into the right branch, okay? So the question is, how do we find the C1 and C2, these two constant? This is a regression problem. So what is the optimal C1, C2? Then you may ask, what is a criteria? What is a loss function we should consider, right? We need to know the criteria. Okay, now let's say, suppose we are using the sum of squares errors. Sum of squares error. So let's say we have a C1 and C2 here. So C1 is the region 1, that's for the region 1. C2 is for the region 2, okay? So that means, this summation means for all the samples that falls into the region 1, using the variable is J, splitting at S, okay? So we want to minimize this, plus for all the samples that falls into the region 2. This is the sum of squares. So we need to minimize the sum of squares from these twos. So what is the optimal value for the C1 and C2? Do you know that? I think this is not a very difficult question if you just do some optimizations. So let's just think about, we have x1 through x10, just 10 numbers, okay? How do you find a C so that you can minimize the summation of the xi minus C, take the square I from 1 through 10, these 10. So what is the constant C that you can minimize the sum of squared errors? So that's the xi minus C, take the square and take the summation for all the 10. So what is that constant C? I think the simplest way is to do what? To do the first order derivative, right? Because this is a very simple mathematics question. To find the optimal value, it's a continuous function, right? You just do the derivative. If you do the derivative, you can easily find out. So to achieve the minimum value, the first order derivative is what? Should be equals to 0, right? So by using that, you can easily see what is the optimal value for the C. C is the average. That's the X bar. It's the average of these 10 numbers. And that is the one that minimizes this. Is that clear? Okay, if that is very simple, then how do we find out the C1 hat? Very simple. It's the average of the response value for all the samples that falls into the region 1, R1. And what is a C2? C2 is the average of the response value for all the samples that falls into the region 2, R2. So you can see when we do the exhaustive search, the C1, C2 are very easy to get. It's just the average. And then it searched for all the variables and at all the unique splitting points. And you may ask, how do we find the splitting point? There are so many, but don't forget that we only need to find the splitting point that only takes effect at the unique value of that x values. If there is no, so it's not on a fine grade, it's only testing the splitting from the smallest that that variable's value to the largest. So it's only using the number of unique values for that x variable. Okay, so it's very quick. It's a very fast algorithm. And when I was a graduate student, that I learned these tree diagrams, my teacher told us that if you really want to know what is a tree algorithm, you write a code from the scratch, and then you will fully understand what is a tree algorithm. And I wrote that code in R. It's not difficult to write. And after I write it, I fully understand that. Okay, so the exhaustive search actually is very quick. Just update the means, and then searched for each x variable. We start with the smallest, so we put them in the order. We start with the splitting at the smallest value, called, let's say, x1, goes to x2, x3, until the maximum, and do the splitting at these unique values of these x. And then you will update the y average, and you can easily find the optimal splits. So optimal split basically passing through for each variable, it's passing through all the unique value of the splitting points, and then search for all the x variables. That's it. So you will find the optimal splits that minimize this. Okay, so this is the binary splitting. If you know how to do that, then the rest are very simple, because you just repeated this splitting procedure on each of the two resulted regions until some stopping criteria is met. Okay, so what are the stopping criteria? So the stopping criteria can be like the mean split. In the R, there were a few choices. So the mean split is the minimum size for a node to split. Okay, so let's say if we have the mean split is 20, that means to have a further split, okay, if you want to have a further split, you need to have at least 20 observations so that you can have a further split. If you have less than 20, it stops here. Okay, it stops splitting at these splits, at this node. Mean bucket is the minimum size for a terminal node. So if we have more than 20 here, but when we do the splits, we found this optimal split is containing 15 here and 5 here. Okay, let's say if we set the mean bucket to be 10, then this is not allowed to do the split. Why? Because the mean bucket is 10, but here we have 5. So mean bucket is the minimum size for the leaf, and the mean split is the minimum size for a node to do the split. It's different, okay, but related. And the max depth is another one. So it defines the maximum depth of a tree. So if you set the maximum depth, let's say is 5. Okay, after we reach the maximum split, maximum depth is 5 for this particular line, then we stop at here. But we can do some further split at the other place until we reach the maximum depth is 5. Okay, so this is another one. So these are the stopping criteria. As long as one of them is met, then that line is stopped until all the lines in the tree or all the branches in the tree, they stopped. then we stop that growing tree step 1. Okay, and then after we stopped here, then we move to the step 2. Okay, but before we go to the step 2, let's see some example. So this is the baseball player. So baseball player salary example. So I fitted 2 trees using the rpart function. That's from the rpart library. So we have the log of the salaries and do the based on the hits and the years. So this shows the first tree, and this shows the second tree. So the second tree is from the fit 1. First tree is from the fit. Second tree is from the fit 2. First tree is from the fit 1. Okay. So you can see what is the difference here. The difference between these two trees, the node for here, these are the same, but if we look down, you can see we don't have a split here. So for this one, we have a split here, but for this one, we stopped here. You see that? Why we stopped here? Why this tree stops here? Because we have a min bucket is what? Min bucket is 10. Because if we do the further split here, we will have 36 on this branch, but 7 on this branch. But when we set the min bucket is 10, this split is not allowed in the tree 2. So that's why there's no splitting here. You see that? And also here, if we look at what else, and we also, stopped here. For this one, we just stopped here. We don't do the splits, but this one we do the first split. Why? Because we have the min split is 30. Why we stopped here? Because we have 28 observations, which is below the threshold. So we don't do any splits here because of the min split. But why we can do this here? Because by default, if you don't specify the stopping criteria, the default has much smaller values in the min bucket and the split. If you want to look at what are the default values, go to the help menu. Okay, remember how to go to the help menu to see that. So go to the help menu and you can see the default value for the min bucket and the min split are very small. Okay, so that just gives you the idea of the effect of setting those stopping criteria in the step 1. But these are the step 1. It's not pruning. Okay, so the step 2 is pruning. Now let's see. So how to prune a tree? So to prune a tree is after the step 1, we usually get a very large tree. It usually overfits the data. Like here, this tree is probably overfits the data because we just reached. We only stopped when the stopping criteria is met, right? But then how do we prune back? So prune back is based on these cost complexity criteria. Okay, so look at this criteria. What is the first term? Okay, for the first term, there's a notation. What is this notation? This notation is the tree size. So T stands for the tree. We have 2 vertical lines here. This is the tree size. This is a notation for the tree size. Remember, what is tree size? Tree size is the number of leaves. Let's say, what is the tree size for this tree? How do we find out? So the tree size is what? 1, 2, 3, 4, 5, 6, 7. So the tree size for this one is 7, right? So that's for this tree, we can say for tree 2, this is a tree 2, okay, equals to 7. Is that clear? But what about this? This is a much larger tree, right? 1, 2, 3, 4, 5, 6, 7, 8, 9. So we have 9. So for this tree, tree 1 equals to 9. Okay, so what is the depth of this tree? Of tree 2? the depth, you can see what is the maximum number of splits. It's probably here, right? So let's see, we have 1 split, 2 splits, 3 splits, and 4 splits. So the depth of the tree is 4. Okay, so that's just a brief review. So we have these cost complexity of, so this is the summation from 1 through the tree size means what? At each terminal node, at each leaf, we have a summation of that. So within the summation, this is what? This is the sum of squares errors for each leaf. Is that clear? You see, here we are talking about the regression tree, okay? We will talk about classification tree in a minute. But for the regression tree, this is sum of squares for that leaf. And then we do the summation for all the leaves. Is that clear? So if you understand that, then what is the first term is about? The first term is the overall sum of squares error, SSE, sum of squares error. Is that right? So the first term is just overall sum of square error. That measures how good the tree model fits the data. How good the tree model fits the data. And what's the second term? Remember, this is the tree size. That's the complexity of the model multiplied by alpha. We see that term, we see that form a lot in this course. The first one we see is the AIC, BIC. Remember, we replace the first one by the -2 log likelihood. That's called the deviance. Also measuring how good the model fits the data. And we see like the lasso, ridge, that's the sum of squared errors. And we also see what? We also see the smoothing splines, right? So anyway, the first term is about overall how good the model fits the data. And the second term is the penalty on the model complexity. So that's the penalty term, right? So you can see this, all these. So what is the best way to learn statistics or machine learning? You just get the main idea. The main idea is just a few main ideas, like the bias variance trade-off, like the regularization idea that we talk about here. How to evaluate how good the model is. It's always a trade-off. First, we need to have a good model that can fit the data well. But only that criteria is not enough. Why? Because that leads to overfitting problem. So we also need to have a trade-off term. We don't want the model to be overfitting. So we don't want to have the model too complicated. So we need to have a penalty on the complexity, right? So that's the balance. But the question is, how do we control that balance? And that's the tuning parameter alpha. You see that? That's the tuning parameter alpha. So alpha is like the lambda in the lasso and the lambda in the smoothing splines and like that. So we can tune the alphas. So when the alpha is large, that means the resulting tree will be simplified. Why? Because when the alpha is large, that means we put more penalty on the complexity of the tree. So the resulting tree model will be simple. When alpha is small, the resulting tree will be complicated, right? So it's just alpha. And how do we choose the alpha? Cross-validation. So you can see the main idea is very simple. Bias variance trade-off, regularization ideas, that's have the how good the model is and the penalty on the complexity. And then we have a tuning parameter to tune that balance. And then we can use the cross-validation to do that. All these methods that we talk about, like smoothing splines, lassos, these, same idea. So the underlying idea, if you know that, you will learn all these methods very quickly. And if you take any deep learning course, you will see, oh, yeah, that's exactly the idea that I learned from data mining course. So, the best way to learn this is to catch up those main ideas. And then you can easily see what's going on here. So for each alpha, we can find a subtree. What is a subtree? Subtree is very simple, just collapse any number of internal nodes. If we collapse any internal nodes, then that becomes a subtree. Okay, so just like here, if we collapse these nodes, then this just becomes the leaf. If we collapse these nodes, then there's no these two leaves, just this one leaf. But we can collapse any numbers. This just one, can be two, and so on. So we can have a sequence of simpler trees. Okay, then which tree we should use? Right? So for each alpha, if you give me an alpha, of course I can find a tree that can minimize the cost complexity criteria. Is that right? So if I have a sequence of trees and you tell me alpha is that, let's say alpha is 1, okay, then that's fine. For each tree, I can find its overall SSE. And for each tree, we have a tree size, and we can calculate the C alpha T. That's the cost complexity criterion for each tree. And we choose the one that gives us the smallest value on the C alpha T. And that's the optimal tree. But that optimal tree is conditioning on that alpha value, right? And how do we choose the alpha? Cross-validation, okay? So that's the idea of growing a tree. Okay, if you know that, then let's see some examples. So this is the revisit of the baseball player example. So here this is unpruned tree. Okay, so this is not pruned. And you may ask, what? Wait a minute, this tree, it looks very different from these trees. Because for these trees, you can see the depths. You can see each branch has the same length, same vertical length, right? And this is to show you the tree. I have an option called equally spaced or not. Okay, so this is this. But for these trees, you can see it's not equally spaced. And this looks like not that beautiful compared to the previous tree. But this gives actually more information. Why? Because here, the length of this vertical distance has some meanings. And you may ask, what does that mean? That means the length of that is proportional to how much sum of squares error reduced by these splits. Is that clear? So you can see that by using this year at 44.5 years, we can substantially reduce the sum of squares errors. But for the next one, using the hit, the reduction of the sum of square error is not that much. It's much smaller. It's less than half of these. And for the further one, much smaller. So you see that? So that's the unequal space, but that vertical distance is proportional to the reduction of the SSE contributed by each split. So that's actually is more informative, but is not as good looking as the previous. Okay. Okay, now so this is from the step 1, not pruned. It's overfitting. Okay, now let's see how do we do the prune. So we can run the cross validations. So this shows the green one is the cross validation errors based on different tree size. Okay, so you can see, and this is the mean squared errors. So you can see the cross validation error on the tree size. You can see what is the optimal one that minimizes the cross validation error. It's the tree size around 3, right? And the training one, that's the black curve. You see when the tree becomes more and more complicated, it's monotonically decreasing. So that's why you cannot use the training errors. But the validation goes a U-shaped. And also the test error is the orange one. You can see the test one actually agree with the cross validation. It seems to me that the tree size is 3 is the best. It also minimizes the test error. And you may say this one could be better than this. But this one, remember, this is much more complicated. And the difference between that in terms of the sum of squares error is not that much. But this tree is much simpler, only 3 size. So the tree size is 3. That means we have a tree looks like that. Only 3 leaves, 1, 2, 3. So this is a very simple tree. But if we have 10 leaves, that's a much more complicated tree. So I would rather choose this one, right? Okay, so now let's talk about the classification. Classification tree is very much the same as a regression tree. The only change in the tree algorithm is the criteria for the splitting nodes and pruning the tree. Okay, so classification tree use the majority vote to classify the new observation falls into that node. And the criteria that we used to measure how good the model is for the classification tree are these 3 commonly used measure for the node impurity. So one is the misclassification error, the other one is Gini index, and the third one is the cross entropy. Okay, so misclassification error, that's very easy. You know that's the percentage of the misclassified observations. And this one is good for the interpretation, very easy to interpret, and also connected to the really directly connected to the quality of the prediction performance. But for the Gini index and the cross entropy, they are not that easy to interpret. But the good thing is that Gini index and the cross entropy, they are continuous. For the misclassification, this is discrete, but these two are continuous. So in other words, from the optimization's perspective, the Gini index and the cross entropy, these are very easy to optimize. But the misclassification, not easy to optimize. Okay, so the most of the tree package, what they does is what? Is for the first step, splitting the nodes in the growing a tree step. They use the Gini index and the cross entropy to do the job in the first step to grow a tree. Why? Because they are differentiable and easy to optimize. And for the second step, when we're pruning a tree, usually misclassification rates are used to guide the pruning. Okay, so that's the difference between the classification and the regression trees. Okay, you don't need to know the details, but that's the difference. Okay, so now let's see an example. So for the heart disease example, we have 303 patients who present with the chest pain, and outcome is binary, yes and no, for the presence of heart disease or not, through a test. And we have 3 predictors. Yeah, so we have here we have 13 predictors: age, gender, cholesterol measurements, and other heart and lung function measurements. And the three of them are qualitative. That's gender, cell, and the chest pain. Okay, so here you can see another good thing for the tree model. A tree model is very tough model. We call it tough because it can be easily applied to the messy data. If the data contains categorical variable, numerical variable, it doesn't matter. It can easily do the splittings. So you don't need to make transformations on the dummy on the categorical variables. These things. The tree can easily handle these mixed type of uh, variables in the data set. Okay, so here we do the cross validation and we find the optimal tree. So an unpruned tree is in the next slides, and then we have the pruned trees. Let's see. So this is an unpruned tree. Okay, so in this unpruned tree, okay, so the for the categorical variables, we have a cell. Okay, so the first split is using that variable. This is a stress test, so Saulian stress test. So when it shows the cell column A, what does that mean? That means it's the first value of the cell variables. Okay, so it has three levels: normal, fixed, and reversible defects. So what is the first one? So the first one is normal. So that means if the stress test, Saulian stress test is normal, then we go to the left branch. Otherwise, we go to the right branch. Is that clear? So that's how it does. Okay, and you may ask, how do I know which is the first value of the cell? Remember, this is a categorical variable. In the categorical variable, in R, we use what? We use a factor for the categorical variable. So cell is a factor, right? So for a factor, you can always use a function called levels. It can show you what are the levels of a variable. So let's say for this cell, if you just in doing the levels for that variable, it will show you all the levels. And the first one appeared, that's the first level. Second one is the second level. Third one is the third level. So if you want to know which is the first, second, and third, you can easily see that through the level function on that variable. Okay, so that's just very straightforward. So this is just to tell you what does that mean. And here, for the chest pain, that's another numeric variable. It has like a B and C. What does that mean? That means it's the second and third value for the chest pain variable. So it has a few categories like here, these are the categories that we have. So second and third are these two. Okay, so anyway, so here I want to point out a very interesting thing is here. Look at this. Rest ECG less than 1, and I do a split. But when we look at the output, it says yes on the left branch and a yes on the right branch. You see that? And that's not the only one. If you look at this one, same thing. We have no and no. Does that seems to be very weird? So here, for that split that I circled here, some splits yield two leaves with the same predicted value like this one. So this split is performed to increase the node purity. Okay, so all 9 patients correspond to the right-handed leaf have a response value is yes. And the 7 out of 11 to the left, they have a response is yes. Okay, so what does that mean? That means we have 9 here, we have 11 here. Okay, for these 9 patients that falls into this, all of them, they have the heart disease. So all of them are yes, they have the heart disease. But for these 11, only 7 out of 11, they have heart disease. And the 4 others, they have no heart disease. So that's why for the majority vote, they are still doing yes and yes, but they are very different. And remember, when we do the first step, growing a tree, which criteria do we use? We use Gini index and the cross entropies. So they are both continuous. So they make difference, even though both outputs are yes. But by having a pure leaf, that actually makes the favors the Gini index as well as the cross entropy. Why? Because you can see that if you are a patient that falls into the right branch, what we say? We say that you are 100%, we predict the probability that you will have the heart disease is 100%. Why? Because 9 out of 9 have heart disease. So we're very confident that the patient that falls into this node will have heart disease. However, if you falls into that node, we're not that sure. We're not that confident. Although we will predict you will still have a heart disease, but the chance of heart disease is only 7 out of 11. So you can see the information are different. Although if you just want to give me yes or no question, they are both yes, but the confidence are different. So that's why I'm just making a point that is, although they both look the same, both yes, but they are different. And also the cross entropy and from the Gini index and cross entropies I, by doing that split, that actually makes the node more pure, and they favor those nodes that has a pure output. Okay, so that's and that phenomenon is quite often in the classification tree. So just be aware of that. And then let's see the cross validation used to find out the optimal trees. Okay, so we have the test is the green one, and the cross validation is the orange one, and the training is the black one. Okay, so you can see the training goes monotonically decreasing, but for the cross validation and the test, it drops and then stabilizes and then goes a little bit up and then have some fluctuations. So the optimal one that based on the cross validation we choose is having 6 leaves. So the tree size is 6. So that's this one. So this is the one that minimizes the cross validation error. Okay, so that's the pruned tree. Okay, so if you compare, this is the pruned tree and this is the original tree. Okay, so pruned tree is much simpler, right? So that's how we fit a tree model. Okay. Okay, so now the question is, we talk about the linear models, we talk about the tree models, and they seem to be very different, right? So which one we should use, right? So here you can see in the top row, we have, this is a classification, okay? We have a green class and a yellow class. So the boundary is linear. So here for this one, let's use a linear model, linear classification model, like a logistic regression. So this seems to be the best. But if we use a tree model, it will do the splittings and to approximate that linear boundary, but the effect is not that good, right? On the other hand, you can see the bottom row, the true decision is actually nonlinear, like a square corner. So in this way, we can easily fit a tree model to have a good approximation of the true boundary. So it really depends. So sometimes the tree works better than the linear model. Sometimes the linear model works better. It really depends on the underlying true relationship between the x and y. Okay, so here, this is a automobile example. We have 60 makes of cars, and we measure their weights, and we want to use the weights to predict their MPG. So the response is MPG, input variable, explanatory variable is weight. Okay, and you can see these circles are the 60 cars observed data. Okay, so you can see here the tree, I fit a regression tree. That's the regression tree. And this is the corresponding tree function in the XY plot. So you can see like this region. What is this region? This is the region that weights is what? Is the lowest, right? So this is this region. So this corresponds to this region. You see that? And what about this region? The second. So for this, you can easily pick one, right? So this will be this one, corresponds to this. And for this one, goes to here. And for this one, goes to here. So you can see each leaf corresponds to a particular region. So you can see what is a tree model looks like in the one dimensional if we just have one x variable. It's like a step function. It's like a step function. You see that? So they use a step function to approximate a linear function. So you can see from the plot, there is a linear relationship between x and y. Is that right? And in the tree, of course, you cannot fit a linear model using a tree. So you use a step function, okay, to approximate that. So that's just a regression tree. But although using a regression tree in here, the R square is about 74%, which is even higher than a linear regression model. Linear regression model R square is about 71.9%, but this one is over 74%. So the tree sometimes can beat the regression model, the linear regression model. Okay. So now, let's we're running out of time. So I will stop here. So I will continue next time. So read the slides and also the case study. I've already posted the case study. So we will finish the tree and the case study next time. So I've already posted the homework for. Don't forget to work on the homework for. It's due next Thursday. Any questions before we stop? Okay, let's stop here.